Hello, hello. Welcome on the side stage. Right now we were gonna have a presentation from Jakub and then another two lightning talks. So please welcome Jakub Mielczarek on the stage.
Thank you. So thank you for coming. Let me start. So basically the purpose of the talk, which is I think the only quantum talk here at this conference, is to provide you certain understanding of certain risks which are related to quantum computing, okay, which might specifically have application in the context of blockchains, etc. Okay. So let me start with the overview of the areas of application of quantum computing in cryptanalysis. So this actually concerns all aspects of cryptography. Okay, so symmetric ciphers, asymmetric ciphers, hash functions, authentication, etc. I don't have much time here to go into the details of all those crypto systems, but I wanna focus on three main algorithms, okay, which have application in quantum analysis, quantum cryptanalysis: the Grover algorithm, the Simon algorithm, and the Shor algorithm. Okay. I would love to go deep into physics here, okay, but I want to stay at a certain level of, of understanding of the cryptanalytic methods. But I have to introduce one thing, okay, from I would say the quantum world, which is quantum oracle. Okay, we already heard about oracles here before, but I want to explain you more or less what the quantum oracles are, what we understand by this. So basically, if we have a register, like in a computer, we have a certain set of bits, okay, we execute certain operations. So in the quantum world, we work on the quantum register, and if we split it for two pieces, the X and the Y part, then we perform certain operations. This corresponds to a certain unitary operator. And then the X part remains unchanged, but the Y part is evaluation of a certain binary function on X, and this is XORed with Y, okay? And this operation has profound consequences for quantum algorithms, and specifically quantum cryptanalytic algorithms, okay? So let's imagine in particular that your function f is your symmetric cipher, where the X argument is a key, okay? So, and then you fix a message, okay? So you have a certain plain text, and you can encrypt it with certain symmetric ciphers for a given X. Okay, so this is one particular application. I will show you how this will go to a certain nice features. And then there's an important aspect that this function f, the laser doesn't work, sorry. This f function might be either a certain external function, okay, let's say we have some encryption machine, and we can probe this function externally, but we don't know an exact formula for this function, so this is kind of external access. And we also can consider a second case, which is the internal access, so we can embed this function in the structure of the quantum algorithm. And it turns out that this second case is much more interesting, okay? And this in particular allows to perform certain quantum attacks like a CPA attacks. And I'm gonna to focus on this Q2 case, which allows for, in a general class of quantum attacks, which are called superposition attacks. In quantum world, if I would have to just point out that the most striking difference between the classical computing and the quantum computing is the quantum superposition related to a quantum parallelism. Okay, so if you have a classical computer, let's say you have 64 bits, okay? Then at a given moment of time, you process this 64 bits, okay? Go on. What you can do with quantum computing is that you can generate a superposition of all possible states of this register, okay? And process that in parallel, okay? And this is the most striking difference between what you can do classically and what you can do quantumly. So for instance, just with a single operation, a sequence of the so-called Hadamard gates, you can produce from the initial state of the quantum register all possible configurations. So let's say that you have a key, you have 256 bits key, and just in one step, you can generate a superposition of all values of this key, okay? Something what is completely impossible to imagine in classical world, because that would mean that you would have to have 2 to the power of 256 parallel processors, okay? But here we just do it on one quantum processor in one step, okay? And then, for instance, if we return to this quantum oracle, and we apply this set of Hadamard gates, just a one step, very simple operation, what you get at the end is just a superposition of all keys and the corresponding ciphertext, okay? And this is an example of the quantum databases, okay? And now the task is, let's say, if you have a chosen ciphertext attack, you just have to select or you have to find out the one corresponding to this part, and then immediately you find what the key is, okay? However, it's not always such obvious thing, even if you have the quantum databases, but there are certain algorithms. The basic one is the Grover search, and actually this algorithm already allows you to reduce the complexity, computational complexity of the problem from the 2 to the n, so the classical search, if you have a database basis of 2 to the n elements, okay, you just have to go through them, okay? So this is basically the complexity of the classical problem. In quantum world, you can reduce that complexity using the Grover search algorithm by a square root, okay? This is something, but this is not the best we can do, okay? And other options, and this is the first example of such algorithm ever made. This is the Simon algorithm introduced in the early 90s, allows us for exponential speedup. So not only a square root reduction of complexity, but the exponential decrease of complexity and increase in the performance. And this concerns a certain problem, okay? Let's imagine that we have a certain binary function and that we have a collision for x1 and x2 with a promise that this is satisfied only if the XOR of this x1 and x2 gives us a certain bit string s, okay, or 0, okay? And Simon's algorithm allows us to find that s, okay, string in exponentially faster than classical time, okay? This is amazing thing, and this is just this simple algorithm. So you have this set of Hadamard gates, we have this quantum oracle, and once more the set of Hadamard gates, and this has application in cryptography. Specifically, if you have a simple block cipher in which you have a certain, typically when you introduce a key, you just XOR it with your message, and then you have some permutations. So the even-Manzur cipher is the simplest block cipher that you can imagine. And in this case, it has been shown already 12 years ago that you can introduce such a functions that this that this S string corresponds just to key 1. So you can just exponentially fast get the key. Then one of the basic building blocks of symmetric ciphers are facial networks. That was based on that. And there's a lot of security proofs for that. And important thing is that here, if you have a 3 layers, 3 rounds of Feistel, you can do the quantum attacks on that using the Simon's algorithm. But then, this is quite a recent thing by Hoshimada Iwata, that if you already have 4 rounds, you can prove that this will be secure with respect to that attack, okay? So this works, however, in one site for chosen plain text attack, but not for the chosen ciphertext attacks, okay? So this is still in progress. The Shor algorithm, perhaps if you heard about quantum cryptanalysis, mostly you refer to Shor algorithm, because the Shor algorithm applies to asymmetric ciphers. And actually, the Shor algorithm generalize the Simon's algorithm. Actually, the Shor was reviewing Simon's paper and based on that wrote his paper, which actually generalized this kind of periodicity of a function in terms of XOR operation to just operation on integers. And this provides exponential speed up in the process of finding a period of a periodic function. And this has direct, I would say, application to the factorization problem or finding the generators of cyclic groups, okay? So this has application specifically to the elliptic curves in cryptanalysis. Okay, so this is a theory, okay? So this is a theory. We know it. We have those algorithms since mid-90s, okay? Already 30 years, okay? But the thing is, okay, what can we do with that, okay? And what is basically the time scale where we can really scare of this algorithm, okay? So this is something I want to discuss right now. And I want to start with a certain trends, okay? Because if we look at the trends, we can try to make some extrapolations concerning future, okay? So this is a trend concerning qubits. These are basic, I would say, degrees of freedom of quantum processors. And you have a different, but this is kind of a different architecture of a quantum computer. But then we have a Rigetti, a Google, IBM. And what we can actually infer from that is that there is more or less a tenfold growth in 5 years, okay? But this concerns physical qubits. So those physical qubits, which might be ions, for instance, in the trapped ions. But then, in real life, they are very noisy, okay? There is a lot of impact of environment, which is killing the quantum coherence. And then, because of that, you have to apply quantum error correction codes, which consume part of those physical qubits. So eventually, the number of logical qubits, those which are used in actual algorithms, it is much smaller, okay? So this is just to keep in mind. But the qubits are not enough, okay? From one side, we have the number of qubits, so this is like a size of the quantum register, but then there is also temporal part, which means how many layers of the quantum algorithm we can perform. And currently, actually, the main limitation on quantum computing progress is because of this temporal part, because this is related with the coherence time, okay? And the coherence time is extremely limited currently, okay? We have some microseconds depending on the technology, okay? And we would like to have more, okay? If the coherence time is shorter, is done, you know, the time that you need to execute your quantum algorithm, you will get mess at the end, okay? That won't work. And this is, in most of the, you know, superconducting quantum computers, we can just perform a certain number of layers, like 20 layers, 15 layers, and after that, you get mess, okay? And there's no kind of reasonable prediction, reasonable outcome. And there are measures introduced to quantify, to benchmark quantum computers with respect to taking into account all those dimensions, the spatial, the number of qubits, and also temporal, how deep the quantum circuit could be. And this is in particular the quantum volume related to, I don't want to go into the details because of lack of time, but this is more or less related to a sampling from a certain quasi-random circuit. And concerning the quantum volume, we have increasing trends, hopefully, and specifically the highest values of quantum volume are currently obtained for ion traps, okay? So these are ions which are trapped in a certain electric trap, and because of that, they are not coupled strongly to environment, okay? And the coherence times can be microseconds, hundreds of microseconds even, okay? And in that case, for the moment, Quantinuum company developed a quantum computer which reached 1 million quantum volume, okay? And you see that there is a geometric increase, so on the logarithmic scale, on the right-hand side, you have a logarithm of quantum volume. We have more or less a linear trend, okay, with a tenfold increase annually, okay? But this number, 10 to the 6, might look already pretty big, but just to understand it, you have to take a logarithm of that value, and this gives you roughly 20. So what does it mean? How to interpret that value? This means that currently, with this quantum computer, the biggest quantum circuit, a general quantum circuit that we can execute on that computer will involve 20 logical qubits and the 20 layers. We cannot go further, okay? That's the maximal thing that we can do on this quantum computer. But actually, this quantum volume is something that I can emulate on my smartphone, okay? So this is still not much, okay? Because the Hilbert space, the so-called Hilbert space associated with that is 2 to the 20, so this is roughly 1 million, which corresponds to this quantum volume, actually. And then you operate on the matrices of the size of 1 million over 1 million, and this is still something the smartphones can do, okay? But based on that observations, based on that trends, let's attempt to make some forecasts, okay? Let's make some forecasts. And so we can assume that, okay, that's something very, under many assumptions. We're gonna make a linear extrapolation, okay? We're gonna see if those trends would be conserved more or less, okay? But there can be different, factors appearing in time. But if that happens, okay, what will be the increase of number of physical qubits and the quantum volume in time, okay? So if you start from now, you go 55 years from now with those linear extrapolations, okay? In 2050, we're gonna have more or less 10 million physical qubits, and the quantum volume would be like 10 to the 56, okay? But this looks huge, but as I said, what matters is really the logarithm of that value, which gives more or less 200, okay? So that means that in 20, if that will hold, that progress, the rate of the progress will hold, in 25 years from now, we will be able to execute a general quantum circuit of the size 200 qubits and 200 layers, okay? Of course, this is something we cannot do with classical computers. If we already have 50 qubits, this is something that we cannot do, okay? And we can do a lot of interesting stuff with 200 qubits and 200 layers, okay? But not necessarily at a quantum cryptanalysis. And this is something what I want to show you. Of course, this is very speculative, but if we go even 25 years further with this extrapolation, okay, you will get like a 350, okay? Okay, so what are the threats right now with respect to that possibilities, okay? Let's first focus on symmetric ciphers. So first, with respect to the symmetric ciphers, in general case, like for AES ciphers, which are current standards, we don't have security proofs with respect to the quantum attacks. We have security proofs for certain simple models, okay, of the block ciphers, like a Luby-Rakov cipher. However, an observation that you can make is that for any cryptanalysis method, the prerequisite for implementation of the attack is to implement that, that cipher in the quantum register first, okay? You always have to do that, okay? Whatever the further step would be, okay? And based on that, I formulate the so-called a strong security sufficient condition. So if you cannot map your cipher into the quantum register, there is no way, of course, to make quantum cryptanalysis, because this is kind of required condition for that. So then, whatever the further step would be, you need implementation of your cipher into a quantum register. And then take a look for AES 256, current standard, the strong symmetric cipher, okay? And currently the most optimal implementation that we know in literature, okay, requires roughly 600 logical qubits and 1,000 layers, okay? We cannot go better, okay? So the logarithm of quantum volume in this case would be at least 1,000, which would correspond to that deep, but perhaps will be higher, but not higher than 6,000, okay? But if you compare that with these numbers, these are still orders of, just like an order of magnitude difference, okay? Asymmetric ciphers. Here, for elliptic curve cryptography, RSA, Diffie-Hellman, etc., all crypto systems which utilize logarithm-based ciphers, discrete logarithm-based ciphers, you can apply the Shor. There was a lot of work on that. In 2019, authors have shown that you need at least 10 million physical qubits and 8 hours of coherence time. If someone is saying 8 hours of coherent time, when we are in the microseconds currently, this is like a crazy thing, okay? 8 hours is really hard to imagine, okay? But anyway. So, but then you can also do the similar analysis as I did before, utilizing the quantum volume. We have currently the most optimal implementation of RSA has these expressions for the number of logical qubits and the number of layers, and based on that you can do a predictions on the requirement on the quantum volume, and this is at least 6,000, okay, for RSA. I mean, for strong RSA with 2048 bits of a key. So, concerning the linear extrapolations, I would say the current trends, the currently, strong ciphers, both symmetric and asymmetric, might remain unbroken within the 50 years perspective, okay? So this is not clear that they will. So this is not yet behind the corner, okay? This is not like someone, there are headlines that there's a quantum threat. This is not yet, honestly, behind the corner, okay? And according to also this methodology and other, they might remain still unbroken in the 50 years perspective. However, something can happen meantime, okay? They might be some technical, scientific breakthroughs, okay? And this progress will speed up, okay? And of course, this is like one order of magnitude difference between that condition and the number that we predict, okay? So still, there is a risk that in 50 years, those ciphers can be broken, okay? So if you collect certain ciphers, they might be broken in 50 years from now, okay? And this is still a threat for certain types of, of information, certainly the information with the long lifespan, okay, classified information, and etc., okay? And the question is whether we have some solutions, and yes, the cryptologists are working on that since already some time, like 20 years, and this is PQC, the post-quantum cryptography, which is attempt to construct a counterparts to the, RSA, elliptic curve, but just to make it resistant to those attacks, okay? Importantly, from the perspective of complexity theory, RSA, SEC, Diffie-Hellman, they belong to the bounded quantum polynomial complexity class, which is the class of the problems that can be effectively solved using quantum computers. And currently the trend is to build specifically asymmetric cryptography based on NP-hard problems, okay? So the problems which cannot be addressed effectively even with quantum computers, okay? And there's a lot of directions. One of the direction is lattice cryptography, highly dimensional, like a lattice structure, okay, like a discrete vector spaces, and there are problems which are considered to be NP-hard, like shortest vector problem or closest SVP and CVP problems. And based on that, over the last 6 years, the process of selecting new standards for asymmetric cryptography was ongoing. And 2 years ago, crystal Kyber, crystal dilithium, which are lattice problems-based asymmetric cryptographic algorithms were selected. Also Sphinx, which is based on the security of hash functions. And just recently, last month, finally, after those years, we have officially first 3 PQC standards. Okay, so these PQC standards are announced, and now you can adopt them, okay? US administration will replace, the asymmetric ciphers in the TLS and etc., okay? So this is a process that will be now, which is now triggered, okay? Everything will be, with time, replaced. So actually, with the FIPS 203, we actually replace the Diffie-Hellman. So there will be no more Diffie-Hellman, okay? We just have encapsulation schemes rather than key establishment, okay? Like a ECDH, which is popular also in blockchain applications. So RSA, SEC, the signature schemes will be also replaced, okay, based on that, okay? And this is a progress. This is kind of the process which is currently ongoing. So just to summarize, okay? So quantum computing methods utilizing the properties of quantum physics certainly provide a potential threat, okay, to some of the currently used crypto systems, okay? We know that since 55 years now. However, there are, technical obstacles with implementation of that crypto systems, okay? The process with development of quantum computing resources is ongoing. It's speeded up over the last 5-10 years a lot, okay? But still, with respect to those applications, the quantum volume, number of qubits is so big that this would require 40, 50, maybe even more years from now, okay? But to really, make a precise assessments on the security in terms of quantum cryptanalysis, of course you have to understand the quantum hardware very deeply. Okay, this is really an important and challenging aspect to really understand all the limitations and all the possibilities which appear, which might lead to some breakthroughs, okay, in like 25 years or 20 years from now, okay? And for some types of information, as I said already before, characterized by long lifespan, quantum cryptanalysis should already be considered in the risk assessment, okay? So if you have some sensitive information, also including some financial information, medical information, okay, government type, military type of information, already those factors are taken into consideration, okay? And we are in this kind of nice situation that certain countermeasures can already be implemented. And this is specifically the PQC, post-quantum cryptography. We already have standards since less than a month, okay? These are official standards, okay, to be implemented. And there is a lot of activity on that. I'm not sure how much of this is happening in the blockchain community, honestly, because I'm from a slightly different community. And there's also a lot of happening concerning quantum key distribution, which is another possibility which provides you a security with respect to those attacks. But let me also mention that even if we have a PQC standards, there are still certain subtleties on that. People are still working on that, okay? Specifically with respect to the lattice cryptography. Not everything is yet clear with respect to the security. And there are no, I would say, direct security proofs. So still there is a lot to be done and improved there. And some links to the features that I used. Okay, thank you. Some questions? I don't know.
Yeah, we have time maybe for one quick question because there will be next talks. And yes, Jakub, are you with us for lunch?
I'm here.
Okay. So maybe I will ask later. Okay. So
I don't know nothing about quantum computing. I'm just curious. Is there such a thing as a quantum randomness?
Yeah, definitely. I mean, so actually, the quantum randomness is, as we think, is the physical. This is a physical type of randomness, and the best randomness that we can even create in physical reality. This is actually the quantum randomness, and even more, we can prove certain properties of that randomness, and this quantum randomness, which is an outcome of the superposition principle in particular, that you have a superposition of 0 and 1, and then you make a measurement, and even 1/2 probability you have 0 and 1. You can extend this to the quantum registers. And currently, you can already buy quantum random number generators just off the shelf, okay? These
like
are
a hardware piece?
These are hardware pieces, okay, using quantum optics. This is already in use. Even in Poland, certain solutions of this kind have been developed and they are available, okay? This is one of the most active area of quantum cryptography, quantum random number generation, okay?
Okay, thank you, Jakub.
Thank you.